Cool. Thank you very much.
Hi everyone. Today we're going to talk about base nets, which are actually a way to represent probability distribution between variables. And the nice thing about it is that it encodes causal relationship between these variables, and it offers us nice tools to represent the probability in a compact way. This is one of the most used examples when people explain base nets. So having sinus inflammation can be caused by either having the flu or having an allergy reaction, and having a sinus inflammation can cause headache or having a runny nose. Okay, so this is one way of representing the causality between having a runny nose and having the flu, for instance, while modeling other variables at the same time. So we've seen in the course before the notion of conditional independence. So conditional independence, two variables x and y are conditionally independent given z if their joint probability given z is equal to probability of x given z times probability of y given z. So for example, if we take this smaller graphical model, which says that basically flu causes sinus inflammation, sinus could cause runny nose, then the probability of having the flu is not independent of probability of having a runny nose. But if you know that you have a sinus inflammation, then these two variables, f and n, become independent. If we have this other dependency relationship or causal relationship, which is like a common cause for two variables, so you have S causes either N or H. So N and H are not independent. But if you know S, then N and H will be independent. Another type of relationship you can model with graphical model is if you have a common effect. So both F and A cause S. And so F and A by themselves are independent. But if you know S, then F and A are not independent anymore. And this phenomenon is also known as explaining away. So for example, if you know that you have a sinus inflammation, then the probability of having the flu is high. But if you know that you have a sinus inflammation and that you have an allergy reaction, then the probability of having the flu becomes lower. Another example is, also if you have a school that accepts people based on scholastic aptitude and sports, for example, so these two variables, being good at school and being good at sports, are independent. But if you know that someone is accepted, then the probability of and if you know that they are good at school, then the probability of them being good at sports becomes lower. Okay. So these are like the basic building blocks for graphical models. Stop me anytime if you have questions. So now we're going to write the joint probability distribution over all of those variables that were in our model. So if we have variables from x1, x2 to xn, then we can use the chain rule of probability to write the joint distribution in this way. So it's the probability of x1 times the probability of x2 given x1 times the probability of x2 given x3 given x1 and x2, etc. until the probability of xn given all of the other variables. Is that clear? Okay. So if we look at our variables, and we start from the top and go down to the children. So and if we use the chain rule, then the joint probability of all of those variables would be P of f times P of a given f times P of s given a and f times P of h given f, a, and s, and times P of n given all of the other variables. And so if you look at this last term here, this will be a probability table with 2 to the 5 entries, because every one of those variables has either a 0 or a 1. Okay? So this will become exponentially big very fast. And so the nice thing about this graphical model representation is that you're going to be able to assert dependencies between those variables and reduce the size of probability distributions that you have. Okay, so the local Markov assumption is that a variable x is independent of its non-descendant given its parents. Okay, so headache is a non-descendant of nose. So nose is independent of headache given sinus, and it's independent of flu and allergy also given if you have a sinus inflammation. So if we go back to this way how we wrote the variables, now we can simplify. So for example, we said that n is independent of all of these variables given s, and we do the same for h. H is independent of all the other variables given s, and so we can write now our probability distribution in this way. So it's p of f times p of a times p of s given f and a times p of h given s and n given s. Okay, and so if we take any one of those probabilities, they're actually like a factor table or a conditional probability table. So for each case of the assignment,
What do you mean by non-dependent?
I can't hear you.
What do you mean by non-dependent?
Non-descendant is anything that's not the child. So here, these two are the descendants of sinus, and all of these are also the descendants of. A descendant is another node that has an edge that either is the child of this node or the parent of which is the child.
So I guess sinus is dependent on node.
Yes, sinus here is dependent of it.
Okay.
Okay, but nose given sinus is independent of flu. Sorry. Okay, so we. Okay, remember here. Here we said that. So we have just a simple graph. Okay, so the probability of if you don't know any of the variables, then there's all of those variables are dependent. So the probability of having flu is dependent on f is dependent on n. So they're not independent, right? Once you know s, then this dependency breaks down. It's gone. F and n become independent. Okay. So here, if I know s, then there will be a break between n and the ancestors of n.
Okay, well, yeah, that part makes sense. I guess I wasn't too sure about. So if you have the sinus one, if you give it its parent,
Yes.
then it's independent of.
There's no more variables in this graph, but if there were variables here that were the parents of those, then it will be independent of those variables.
Okay, but like what if they had further dependent of sinus?
First, it depends on what the shape of the graph would look like. So we will have examples in the end, but if here we have, so let's say nose has another descendant, and given nose, sinus will be independent of that descendant.
Okay, but I guess given flu and allergy, sinus is not going to be. It's still going to be dependent on it.
Yes, it is dependent. Because it's descendant, they're not, it is not. So it's only independent of its non-descendants. So for example, n is a non-descendant of h.
Okay.
So given s, it's going to be. Okay? We're going to make do with examples. So here we just have to see that it does simple, we can write this the probability distribution in this simple way, where for every variable we just include its conditional probability given its parent. And this will take care of all of the joint probability distribution. Okay. So if we look at one of those factors, this is how it would look like. Here, every column is one of the assignments to the parent. So if f is true and a is true, then you have two cases for s, of course, and those two values should add to 1, right? Because this is the probability of s given one fixed assignment to the parents. Exactly. And so for these variables that only have one parent, then you have a smaller probability table which has 4 entries instead of 8. Okay. So now we can use this base net representation to make queries and infer, for example, what's the probability of having the flu if you have a runny nose. Okay. So remember, this is a conditional probability. So the probability of f being true given n equals true is the joint probability of f and n being true divided by the probability of n. Okay. So let's find this first. The probability of flu being true given that n is true. Okay. So we're going to do that by looking at the joint that we derived in the previous slide here. Okay, and we're going to instantiate the evidence, so we're just going to fix n to be true. So this will reduce the number of the size of the probability here for n, right? Because we just have one case for n. We pick the true probabilities, and now we're gonna marginalize over a, s, and h. Okay, this is basically what's written here. And so in order to marginalize, we have to integrate or sum over one of those variables. Okay. So let's think about it. The thing is, if we sum over the variable s right now, if we sum over the variable s, we're going to have to sum over those three terms. Sorry, and those three terms contain. Okay, before I go there, let me just say that, okay, whenever you remove a node from this graph, you're going to add another factor instead of this node. And this factor is going to connect all of the nodes that were connected before. So if I remove sinus here, if I remove it from this graph by integrating over it, then I'm going to introduce a term that makes all of the variables that are connected to sinus connected to each other. Okay. And here, if I remove allergy, I am going to introduce, I'm going to have to introduce a term that contains f and s at the same time because of this V structure. So remember, the V structure means, this V structure means that you have a term that does depend on f and a at the same time, on s and f and a at the same time. So once you integrate over a, you're going to obtain a term that has s and f at the same time. So in order to, so you can see how, depending on which order you pick to remove those variables, you can end up having a lot of extra edges to this graph. So if you remove sinus in the beginning, you are going to have a lot of extra edges because all of the other variables are going to be connected. So in order to know the ultimate way to pick the order in which you're going to remove those variables is to first moralize the graph. So moralizing the graph means for every V structure, so for every common effect structure, you connect the parents with an edge. Okay, so this will make it clearer which variables are connected for you to be able to assess the complexity of, or the cost of removing any node. Okay, so they call it moralizing because you're married to the parents of travelers. And now we're going to choose an optimal order. So let's say I start with S. If I'm starting with S, then if we look at the probability distribution from before, these are the terms that contain S. And so if I'm going to average or marginalize S, I'm going to obtain a function of three variables H, A, and F. Okay? There's no N here because N is fixed to just one value. That's why N is gone. Okay? Is that clear? But so since this function has three variables, then it's going to have 2 to the 3 entries. So removing sinus in the beginning might not be the most optimal thing because you're going to add those extra edges and have a larger table. Okay. So what if we remove H in the beginning? So this is I rewrote here the distribution. So this is the only term that depends on H. If we take it to the end of the equation, then you can see that we're just adding over all of the values of H given its conditional probability. So this all adds to 1, so we can remove it. So we already got rid of one node that was going to be bothersome for So now if we remove s, remember because nose just has one value, then we are going to obtain the terms that depend on s are these two. And we're going to obtain a function that is a function of f and a. Because again, n has just one value. Okay, so now this is all that remains for us. So we have to remove a, because we just want the probability of f given nose n equals true. Okay, so to remove a, we're going to sum over the values of a for these two terms. And we're going to obtain a function g2 of f. Okay, so if you look at this, this is actually a probability of n equals true given f, if we're interested in that, because this is the joint probability of f and n is equal to the probability of f given times probability of n given f. Okay. So now the conditional probability of f of having the flu given that you have a running nose is going to be equal to this term here that we're going to get from this table over the probability of n equals true. And we get the probability of n equals true by marginalizing over the values of f from this joint distribution factor. So we wanted to, given a certain set of variables, the value of a set of variables, we wanted to know what the probability of f was. We marginalized over all of the variables, trying to minimize the size of the intermediate probability distributions we're going to obtain. And then we ended up with the joint probability of those two variables, and we marginalize over one of them to get p of n. And then we use Bayes' rule to get the conditional probability. Okay, so now we can look at some dependency rules. So if I give you this base net with like this is a common effect here, the other ones are either common cause or like a chain. So are A and H independent? Does anyone know A and H are independent? Anyone? Okay, who says they're independent? Yes. Okay, yeah, it's true. They are independent because here we have a common effect, and we do not know C. And here we have a common effect too, and we do not know C. So this chain here, at least here, the chain is broken, and A and H are independent. Sorry, this is okay. So when are A and H not independent? So in order for them not to be independent, we have to know C here, and we have to know F, or one of the descendants of F. And we shouldn't know the values of these nodes, because these nodes, knowing the value of these nodes will break the dependence between nodes. Okay. So let's just think of what are the rules in order to be able to guess them. So we're going to define what an active trail is. So before I was trying to look between the variables A and H, and I wanted to know if there was an active trail between A and H. An active trail means a dependency along that. Okay. So I'm going to look at the succession of x's from A to H. Okay. And so for every 3 x's, I'm going to see if there's this direction. So if we have this direction of arrows, so all the arrows are pointing to the left, to the right, and xi in the middle is not observed, then there's a dependency. There's an active trail. If we have the arrows pointing in the other direction and the middle node is not observed, we also have a dependency. And if we have the middle node a common cause and the xi is not observed. And finally, if we have a common effect and the middle node or one of the descendants of the middle node are observed. Okay, so any of those 4 cases means that you have an active trail. And if you don't have any active trail between 2 variables, then you can say that those variables are independent, or this is called deseparation. So let's look at a more complicated graph like this one. Okay, so do you think that A and B are dependent or not? Independent. So is it independent? Yes, that's true. Because so here in this path we have a V structure, and we don't observe the common cause, the common effect, and the same thing here. So both paths are clear. Okay. So here, if I observe E, are B and G independent? Yes, they are independent because here E breaks. So here we broke this dependency here, and the other side has those D here. Not observing D here breaks this other trail too. From E to G. Okay, so if I have K, are I and J independent? Yes, okay. So obviously, because we observed the common effect, then it is not independent. So they're dependent here because we observed the common. Okay, it doesn't matter that there's another trail because once there's a dependency, it's okay. So now E and F, are they dependent given K? Anyone want to guess? They're not independent because so I and J here are not independent, and then we have this trail which is nothing here is observed. So this is an active trail to here. Okay. So now if I observe I and I have are F and K independent? So they are independent because this path between F and K is broken because we observed the middle node, and this path here is broken because we don't observe the common nodes. Okay. So now if I observe both I and K, are E and F independent? They're independent, yeah. Yes, because before we just observed K before, and there was a trail from F to K and from E to K, so it was independent. But now because we know I, so knowing I breaks the dependency between F and K. Okay, so if we observe H, are F and G independent? So remember, if you observe a descendant of the node, or in a V structure, then it becomes active. I mean, it's not, it's an active trail, yeah. So this is an active trail now. So from F to G, we can go this way, and there is an active trail. Because once you observe H, then A and B are dependent, and because we didn't observe anything along these lines, then there is an active trail from F.
So the active trail lies between D
Yeah, it doesn't matter, because if it matters. So there's two cases, right? One case is when you have a V structure, so both arrows are pointing to the same node. And all of the other cases, if you don't observe the middle node, it's fine. If you don't observe the middle node, it's an active trail. Okay. So here, A and B are dependent, and because you don't observe E, then B and G are dependent. And the same thing here. So A and B are dependent, and you don't observe C, so A and F are dependent. It doesn't matter that they're going on. Okay? Anyone else? Okay, so what about this one? So I observe A and H, and are F and G independent? Okay, who says they're independent? Okay, who says they're not independent? Why is it independent?
Because I think A breaks up.
Exactly, yeah. So H makes this an active trail, but knowing A, so we said if A is if the middle node is a common cause and you do observe it, then it's not an active trail anymore, right? And this we've been ignoring this lower path because this has a V structure and it's not observed, so this is not an active trail for sure. Anyone has any questions? Do you want to go over some?
Bases have like loops in them. In terms of like I guess A, B, and A. If it was in
You can't have a loop like edges going up. No, that won't be.
directed.
Yeah, you can't. But this sort of loop is fine. Yes.
Could you go over moralizing again? Why
Sure.
we want to do it and why it's not a problem if a node has 100 parents and then we get 100 squared edges between all the parents?
Oh, that is a
Oh, that is a problem.
That's
Okay.
why. Okay, so let's take this example because it's more complex and you can see why. So let's say I want to infer. Okay, I want to infer what the probability of. Okay, we said that. Okay, let's forget about the independent species we assume for now, and we want to infer something about A given E, for example. Okay, so we have to remove all of those edges and just keep A and E in the beginning.
Yes.
So whenever you remove one of those, if you want to remove G, for example, here, you're going to remove G and you're just going to add an edge between J and E.
Yes.
And, okay, but if you remove, let's say K, now there's going to be an edge between I and J, right? If you remove K.
Yes.
Because K's probability distribution is K given I and J.
Yes.
So there's a function that has I and J in it, right? And so you can see that just from looking at the structure of the graph, you can see that removing K will add a node between I and J. Just if you ignore the arrows. You can if you look at the arrows, but
Yes.
if you're just like, yeah. So one way of figuring out that complexity is to add an edge between the parents of each V structure. So once you add that edge, then you can count. So,
Okay, so it's a way of predicting what's going to happen later whenever we remove that edge.
yeah, it's a way of indicating. Yeah, so every clique in the graph is going, or every 3 nodes is going to correspond to one factor over 3 nodes, or one of those functions over 3 nodes. But yeah, it's a way of. It's what you said.
Common cause case. So if we observe B, then well, and we want to find out information about E, we don't have to care about D, for instance. So
No, we don't. That's that. Right? If you remove B, there won't be an edge between. Oh, sorry. There won't be an edge.
don't really have anything to normalize, right? Because you've got one parent and then two.
Yes.
You're gonna also get structured learning in your homework, and so we're gonna cover a little bit of that. I'm sorry about the delay with the camera, but we need to record it since I saw that most people can't make it. Okay, so structural learning was basically covered. Is basically covered in any graphical models class. These particular slides are designed after the slides in fall 2010 PGM taught by Noah Smith. Also, I suggest you read Shai Cohen's recitation notes from fall 2009, also on BaseNet and structural learning. So I put a link to them. You should probably go over them as well. Now, when you know the structure of a BaseNet, all you need to do is estimate the parameters of the conditional probability tables using maximum likelihood estimation. So that's relatively easy, given what you know so far. Now, if you don't know the structure, we're going to go over that today. You can apply things like Chow-Liu. When there's missing data, you're going to have to apply variational methods such as EM, but you're probably not going to cover most of that in class. So you only need to worry about structure learning and estimating the parameters of the conditional probability tables. So when you know the structure, the maximum likelihood estimator for a BaseNet whose conditional probability distributions have disjoint parameters is equivalent to maximizing each conditional probability distribution. Okay. So you're going to have to get the maximum likelihood estimators for the parameters of the conditionals. Now, let's see how we will decompose this. So we want to maximize the likelihood of the BaseNet. So we'll take the product over all the samples given of the values given the parameters. So thetas are the parameters in our graphical model. We can decompose this by only considering the parents of each given variable in the graphical model and theta. Now, if the parameters are, if we've got a set of conditional probability tables and the parameters in each conditional probability table are disjoint from each other, we can split this up into several optimization procedures. So the most common distributions, as you know, have closed forms for the MLE. Now, it's useful to know what distributions you obtain when you condition. So under what conditions does conditioning on a Gaussian also result in a Gaussian? Okay, or when you condition on a binomial, it's important to know what you get. Okay. Now, you'll need to solve to get the maximum likelihood estimator by solving a complex optimization for every parameter. And that's, relatively straightforward given what you know now. Yeah. Yes. So a parameter is something in your conditional probability table. What Layla showed you. So Layla showed you a conditional probability table. Like when you've got got something like when you've got like x, y, and z, you're going to have something like the probability of z given different combinations of yz. So you're going to have 4 combinations for yz, and you're going to have more parameters. Okay. Does this sort of answer? Yes.
So by structure, you mean each of the node are the parents of the other nodes, right? So
Yes.
How do you know?
Well, I'm assuming, so at this point, I'm assuming this is for node structure. So this MLE stuff, I'm going to show you what to do when you don't know the structure. But for now, if you know the structure, all you need to do is get the parameters of the conditional distributions based on the values that you observe. Okay, and that's something that you already have the knowledge for. Okay. Okay. Any other questions so far about? Is it clear to everyone, at least in principle, what you do when you need to estimate the parameters of a Bayesian network? And what the parameters are?
And how do you divide it into?
Yeah, so what I mean is that when you've got a chain, for instance, right? The conditional distribution of, so the probability table that will tell you what's y given x will be independent from this. So this will be a theta 1, and this will be a theta 2. And these are, you'll assume independence, right? So this is what I mean when you decompose a base net. Like when you've got a tree, for instance, everything above this node, like the children of this node aren't going to be influenced by everything above it, right? You're going to have separation. So this is easy to see for trees and chains. All right. So this decomposability only applies when you can actually factor your base net. Okay, it's related to the concept of factor graph, which I'm not sure if you've learned that in Markov networks, but you will learn it. Okay? Okay, questions? Okay, well, I guess we can proceed to structure learning then. So it basically goes on the same principle. We're going to maximize the likelihood of the data. However, we'll need to score structures based on their likelihood this time. It's not sufficient to just score parameters. We're going to have to actually score structures. The alternative is to use statistical tests to determine conditional independence. And you want to construct the direct data cyclic graph that corresponds to those independence, to the results of the independent tests. Okay. Okay, so when maximizing the likelihood for a structure, we're going to consider the structure with its best possible parameters. We're going to take the maximum, that's the maximum likelihood estimation. Every structure will have an optimistic estimator, will be optimistically estimated based on what its best parameter assignment is. So as I said, this is optimistic, but it's still correct if we just want to maximize the likelihood of the data. Okay, so let's see how this works, how we'll derive the structure score. Okay, so do you guys have questions before we start going through the derivation? No. Okay, so we're going to sum over all the variables and consider the empirical probability, the empirical probability distribution of each observed value given the parents of that variable. Here we simply apply Bayes' rule, okay, and then we decompose this this factor here into a part that depends on the parents of xi and a part that doesn't depend on the parents of xi. Okay, by splitting this into and then using the definition of marginal distributions, we get that basically the log likelihood of a structure G is the sum of the mutual information between each variable and its parents, minus the entropy of that variable. Okay? So you can go over, I guess there's not that much time, but you can go over the derivation at home. And you can see that this makes sense.
I have a question.
Yes.
So what is P hat?
P hat. Oh, that's this P hat. Anyway, both P hats are empirical estimators of the conditional distribution or the joint distribution. They're basically just so P hat of I think it's xi and u is basically the number of occurrences of xi and u over m. M is the number of samples. Okay? So you basically just count the occurrences and you get an empirical estimator for that joint distribution. And the same for the conditional distribution. So now let's look at this decomposition. So okay, well I guess is everyone clear so far? Any questions? Okay, so looking at this decomposition, we can see that the second term actually does not depend on the structure. So the entropy of each variable is the same regardless of the structure that we impose. Now, on the other hand, this mutual information term is directly related to the structure. So the more mutual information we have, the more we'll maximize the likelihood. Now, there's a problem with mutual information, and that is that adding information that never decreases the mutual information. So basically, if you've got a variable x and a variable y, and you want to compute the mutual information between them, adding another set of variables or another variable z to y will never decrease your mutual information. So unless conditional independence holds exactly in the data, more connections are always better. So if you actually try to do maximum likelihood estimation for Bayes nets, it's guaranteed to overfit because it will try to put an edge between every two variables, and you'll eventually get a clique. So that's no good. Okay, does everyone understand why this happens? You guys don't seem convinced, so ask questions if something's not clear. Okay. At any rate, we have a way to fix that. So one possible solution is to just allow each node to have at most one parent. So the structure will have at most n-1 edges, and now we'll be faced with the decision of where to place those edges. Now the algorithm will be to consider the mutual information between every pair of variables, and then find the maximum spanning tree of our graph. So there's a finite and not that big number of trees, so we can consider all of them. We're gonna, pick the root and traverse to get the structure. Yes.
So how do you decide whether xi or xj is a child or
the first part of child u, the maximum spanning tree, gives you just the skeleton of the Bayes net. So you're gonna get something like this maybe, and then you can pick any node and say, oh, this is the root, and then a traversal will give you the structure, the direction. It's a tree, so there's no way you can have cycles either way. So you'll just pick a random one to be a root.
Does it affect things?
Sorry?
Does it affect the
the accuracy of what it won't affect the likelihood. Okay, it will just yeah. Okay, you still seem to be sort of confused.
Yeah.
The base nets are equivalent. So this base net is equivalent to this one. Okay, maybe I should redraw this. So when you've got, so this chain and this one are equivalent. Okay? These two are equivalent from the base net perspective. They have the same skeleton. Okay, now I have so pop quiz. Is this the same as the other two? Okay. So I see some people saying no. Okay. So this is a V structure, and it's not the same as the other two. But by using depth first traversal, if your skeleton is just this, using depth first traversal will never give you something like this. Like traversing the base that will never give you something like this. So the algorithm is guaranteed to give you a legitimate tree that will not have these structures. Okay? Alright, so do you guys kind of get what's going on? Okay. So we haven't talked about you know, putting priors on structures or finding consistent scores. So as we can observe, the MLE score is not consistent because when the number of samples goes to infinity, the method will just try to link up every two variables. However, there are scores such as the Bayesian score and the Bayesian information criterion that are consistent. Okay, and we'll also not go over structure search. If you at any point feel the need for us to cover any of these things, let us know and we'll do it. So in your homework, you'll need to build something that's called a tree augmented naive Bayes. And I'll quickly go over that. So as you know, with naive Bayes, you have a classification task and some features. Okay. So this is just a naive Bayes model. And you've already learned how to use it in classification. Okay? So for tree augmented naive Bayes, what you'll need to do is add edges between one variable and these others. So you're going to say that one feature is the parent of all the other features. Oh, sorry. Okay, mistakes. It should be like at any rate. What you'll need to do is estimate the mutual information between each pair of variables and the class, and build a tree on the features. All right. So, do you guys have any questions? Okay. Well, the homework will be out tonight. So if you find the text of the problem isn't clear, please feel